Our analysis of simple harmonic motion implicitly assumed that only the spring force acted, and so energy was perfectly conserved. In real-world systems, some of the energy bleeds out to heat, to friction, or other non-conservative forces. We call that effect damping, and this sort of motion is called damped oscillation. Why is it called damping? Well, it actually comes from how people do it, which is to sort of put your oscillator inside some sort of movable piston. And so there's like a thing here and a spring like this, and there is some sort of fluid filling the piston. Originally water, so it would be damp. And as the piston moves, as for instance, let's say the spring here is going to try and contract, there'll be some force from the spring, but there'll also be some viscosity force, some fluid friction force that acts against it. And as is usual for drag type forces, it's dependent on the velocity. The faster the thing's going, the more it suffers drag. So we bleed out energy, and it's usually proportional to the velocity. All right, so normally a damping force is a drag force, where this constant is called the damping constant, and ends up controlling the behavior of the system. We characterize things based on the size of B. When B is a small number, small-ish, the system is underdamped. It's being dragged, but it's able to move. So it goes through its equilibrium and oscillates the way an oscillator should. But as it comes back, it gets less and less speed, and therefore less. As energy comes out, it will have less and less amplitude because of a half kx square, right? If the energy is going down, then a half ka square is going down, so a square must be going down. And so the amplitude of the motion decreases, even though it's oscillatory, and it's tracked by this so-called envelope, an exponential. The amplitude itself is now a function of t, an exponential function of t. Also, and this is sort of important to know, the frequency also shifts a bit. And we're not going to go into that, but if you grind out the differential equation, you find that the actual frequency of the oscillator is somewhat shifted by the presence of the damping force. Something is critically damped if it never oscillates, but it returns to equilibrium in the shortest possible time so as to not oscillate. So this is the critically damped system. It does eventually reach equilibrium, or at least gets asymptotically close, but it never goes past, so it isn't really an oscillation in normal sense. And then overdamped system, which has large B, never even oscillates once. It returns to equilibrium exponentially, but very, 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 very slowly. And in fact, I think in many systems you might find that it doesn't get back to equilibrium at all, that it comes to rest at some offset. So, in sort of just concerns of the class, the committee doesn't ask very much about damped systems. They kind of want you to know they're out there. They're really happy if you understand the exponential decay bit, that the amplitude is coming down with time. But they don't do any of the math of it, so you don't need to worry too much about the specific form. All right, it's possible to replace that energy that's leaking out by applying what's called a driving force, and these are therefore driven oscillators. As an example, think of a playground swing. There's some frequency at which the swing will oscillate, determined by the length of the chains. And if you pump out, eventually the initial amplitude will bleed out, the initial energy will bleed out, and the swing will stop. But you know you can pump the swing by pushing on the seat. Either someone behind you can push you, or even you can move your legs in such a way as to do work flexing them and putting energy back into the system. Let's talk about the case where, say, some other person is pushing you and getting you to swing. You know that that push will be most efficient when the frequency at which they push is the same as the frequency of the swing. In other words, it doesn't make a lot of sense to push at a much higher frequency because most of the time you're just moving your hand back and forth and the swing isn't anywhere there. And it doesn't really make sense to do it much less because while it might work if you push every other swing, that's not nearly as good as pushing every time you swing. So we want the frequency to be the same, which is what we call a resonant frequency. The system is therefore in resonance. When the system is in resonance, a small input amplitude can produce a very large output amplitude. You can get amplification because even though you're only putting a tiny bit, it's always being added efficiently. All right, we're going to watch that demonstrated here.
Here I have, in this demonstration, 4 sets of rods of different lengths, and they're all connected by this steel base. Now, the question is, if I pluck this large rod, how will the other rods respond? Will they all start to vibrate? Will the vibrations be different depending on the length, or will just the matching rod vibrate? So as you can see, when I pluck this one, the matching rod starts to vibrate while the rest remain steady. This is because when I set this into oscillation and sent vibrations through the base of a certain frequency, the frequency of this rod, which was picked up by this rod since it has the same natural frequency as this one, and started to vibrate. The rest of these rods have different natural frequencies, which are not equal to the frequencies of these rods, and therefore they did not vibrate.
All right, and that's the fundamental illustration of resonance. We'll talk some more about it now and some of its crazy applications, but the fundamental application is that things will tend to vibrate sympathetically at the same frequency that they have. And rigid systems tend to have a natural frequency or a small number of them. So if you can drive them at that frequency, then they can pick up high amplitudes. What goes on in the case of the rods here is that plucking the first rod causes that base to vibrate at that frequency, which does move all the other rods, but not very much, because for the most part, those impulses are being wasted in the rod. They can't couple efficiently, so even as they start to move, they move back and forth at a different frequency. And so you're plunking in, it's going a little bit, but not very much. But the rod's at the same length has the same frequency, so every time it's being pushed by the wave in the bar, it's gaining a little bit. And so that very small little motion becomes very, very big motion. One spectacular view of resonance is the Tacoma Narrows Bridge, a bridge that was built opened in July of 1941 and underwent motions that are spectacular in resonance to what they call vortex shedding. Basically, the wind would blow by and little pieces of swirls of air would break off, and they'd break off at the resonant frequency of the wire, and what happens would look something like this.
One over the USA's Tacoma Narrows. From the day it was finished in 1940, it bounced around. Dubbed Galloping Gertie, it became a tourist attraction. Real trouble started the day it began to twist. The wind wasn't particularly strong, but it stayed steady. Each time it twisted, it turned a little more. Finally, it twisted itself apart and became every bridge builder's nightmare.
So, this behavior could be replicated in the lab.
For Gimsing, the answer could be seen in the wind tunnel. The problem with the Tacoma Narrows Bridge was its sharp, square road deck. As the wind hit it, miniature whirlwinds formed at the corners, which started the twisting. The twist turned the deck towards the wind, which produced more twist, and finally, disaster. The answer, get rid of the square corners.
If you add these airfoils, the wind will move smoothly around the bridge section, just like you'll experience on the wing of an aircraft. In the case of the Great Belt Bridge, we tested a number of different shapes to find out which would give the most stable bridge, and it turned out it would remain stable to a wind speed which is more than twice of what have ever been measured in the Great Belt area.
All right, so the basic explanation of what had happened here is you have the deck, and the wind would come, and because of the sharp corner of the deck, it would curl, and those curls would build up, and eventually they pull off, they spit off. And of course, it'd be going down here, and you get the same kind of curl, and then it spins off. But the problem is that these vortices carry a momentum. So if they're going to carry a momentum off this way, then they're going to kick the bridge that way. And so the bridge was getting these little kicks, and they're not much, but little kicks back this way. And at certain wind speeds, the rate at which the vortices spread off ends up being the resonant frequency of the wire. And so the whole bridge ends up humming and twisting and turning, which the up and down motion was not so bad when the bridge was doing something like this. I know it sounds like it's terrible, but it turns out that's not so bad. But twisting motions are fatal. Just imagine taking take like a paper clip, and just take a steel paper clip, which you cannot break with your hand, and move it back and forth about 20 times, and it will come apart because it's very stressed at that juncture. So this is another take on it that goes a little bit more into the so-called vortex shedding.
And its appearance. Even during construction, it was apparent that the bridge was too flexible, even under moderate winds. Construction workers gave it the nickname Galloping Gertie. Only 4 months after it opened, the bridge collapsed in dramatic fashion. In fact, this failure was so dramatic, there's a good chance you've seen this video before.
Maybe a little upbeat for a bridge collapse.
So what's happening here? You've probably heard of resonance, which is where a periodic force syncs up with the natural frequency of a system. The classic example is a swing. With resonance, small periodic driving forces, like pushing someone in a swing, can add up to large oscillations over time because energy is stored. In the case of wind-induced motion, the periodic driving force comes from an effect called vortex shedding. This is where fluid flowing past a blunt object oscillates as vortices are formed on the backside. When these alternating zones of low pressure occur at a frequency near the natural frequency of the structure, even small amounts of wind can lead to major oscillations. This is why some chimneys are equipped with helical vanes to create turbulence and break up the vortices. The day of its failure, the Tacoma Narrows Bridge did experience resonance from vortex shedding. You can see this in the vertical undulations for which the bridge was famous. But this resonance isn't why it failed. About 45 minutes before failure, a different kind of oscillation started. You can see in the historical footage that right before failure, the bridge isn't oscillating vertically, but in a twisting or torsional motion. The reason for this change in oscillation is still debated, but one of the best suggestions has to do with the aerodynamics of the bridge. Rather than a truss through which wind can flow, the shape of the Tacoma Narrows Bridge, with the large steel plates on either side, created some strange interactions with the wind. Any small amount of twist in the bridge created vortices, or areas of low pressure, in locations that actually amplified the twisting motion. Each time the bridge returned to its natural state, its momentum twisted it in the other direction, where the wind could catch it and continue the cycle. This phenomenon is called aeroelastic flutter. It's the same reason that a strap or sheet of paper vibrates in the wind. It's a completely separate mechanism than resonance from vortex shedding because the periodic forces are self-induced from the naturally unstable aerodynamic shape of the bridge. This flutter eventually created too much stress in the suspension cables, and the bridge failed.
He actually also alludes in this to something which is maybe shocking 80 years later, but we still don't know entirely what happened there. There are still papers being published nearly every year of someone else with their own model on what took down the Tacoma Narrows Bridge. Which is maybe a little disturbing. So everyone's pretty sure that it's aerodynamic and that it's self-induced, but the titles of journal articles remain long and complicated, which is a good sign that we don't really know what's going on. So people invent things like aerostabilized self-induced torsional oscillations, because that sounds impressive and we don't really know what it means. So just keep that in mind. The vortex shedding is definitely an important thing. This sort of self-feedback mechanism seems to also be an important thing. and lets you think that, well, at least, we now know everything, and this is a problem of the past, the same way that like plagues and the earthquakes taking down Rome were a thing of the past. No, like those things, this is also still something. So this is footage from the Verrazano-Narrow Bridge in New York relatively recently, and they had to shut down the bridge, and you can probably see, or maybe more importantly hear, why. What you're hearing here is just the bridge. It's vibrations in these wires. And so each of these wires was being essentially plucked by that vortex thing and vibrating, setting up a wave, well, really like this. Each of them sort of really doing like this, back and forth. And you're hearing that the same way that like a guitar or a harp would go. This is sort of the world's most expensive, largest harp. You can also see the oscillation of the roadbed, the little breathing up and down. Right, you can see how much it moves. More in the forefront. So you can see how it moves back and forth a bit, and so these problems are not entirely gone. Now the difference is the Verrazano-Narrow Bridge is older. It's been there a long time. We know it's relatively stable. It's not a flat truss. It has some other stuff going on, and that there's enough damping going on. People would argue that we at least aren't seeing the sort of weird self-induced counter vortices in the roadbed that were issues for the Tacoma Narrows. But mostly what happens is we've learned some lessons from 1940, and these bridges are constructed with that in mind. All right. The committee, again, wants you to know about the existence of resonance. They will not ask you a lot about it in a specific format, but they might try and find ways of working it into the tail end of free response questions.